I'm really excited to share with you part of my work on signatures um, and their applications to finance and maybe machine learning. Um, so maybe let me start with the most important word in the title, which is memory. So memory matters. Why? Because many dynamical systems exhibit path-dependent behaviors. Okay, you can think of lead-like relationships, events that happen at multiple timescales, or long short memory effects. And mathematically, we are interested in understanding how to model these path-dependent or non-Markovian effects in a tractable way. Before answering this question and looking at the tractable, I would say, or mathematical tools that we have at our disposal to do that, let us start by maybe taking a step back and going back maybe to the big picture. What are we trying to do when we do modeling in applied mathematics or even, and most importantly, in finance? So typically we are in a random environment, and based on some available information, we would like to determine some actions. Um, think of hedging strategies, optimal investment, and this is based on evaluation of some rewards or quantities of interest that most of the time are written as conditional expectations. Okay, you can think of option prices. And typically, what we try to do in mathematical finance, I like to call it summarize and linearize. Okay, we usually try to do it in two steps. So first, we try to identify the good variables, Markovian variables that summarize the information, typically of ft, okay, that we have at time t, so that we can write these conditional expectations as measurable functions of these variables at time t. And in the second step, usually we hope to, in the best cases, to linearize, to have this function that is just linear in the variables, so that we get some semi-explicit or explicit formulas and fast computations. And here, what I mean by linearized, it's linearized in a very, I would say, a broad sense, because in some sense, okay, polynomial function of factor y can be viewed as a linear function on the extended vector of monomials. Okay, if you extend the state variables, um, sometimes you're able to linearize the problem as well. All right. So even some nonlinear functions can be seen as some linear functions. Okay, so keep this in mind for later. So now going back to our question, how can we model these path-dependent effects in a mathematically tractable way? Um, there are several classes of processes. In this presentation, I'm going to focus on two classes, which are Volterra processes and path signatures. So first, what are Volterra processes? They are named after the Italian mathematician Vito Volterra. And I think a very intuitive way to think of Volterra process simply start from weighted averages. Okay, so if you're given a time series and let's say, ask you to predict or forecast the future value of the time series, the first thing you'll try to do is summarize the information and compute some averages or weighted averages. Okay, why weighted averages? Because we would like to put some more weights on the recent past and the distant one, right? This is very, I would say, popular idea in finance, especially, okay, when we deal with time series and non-stationarity and so on. And so basically, we summarize the information using these weighted averages, weighted by some kernels that can be exponential or other type of kernels. And what are Volterra processes? Where they are simply the continuous time analog, if you want, of these discrete sums, right? And Volterra processes can be written in this way as stochastic convolution, okay, against some if you want, process increments of process z. And the kernel k here can be exponential, but also it can be other type of kernels, and this allows us to encode memory and persistence by playing on the kernel. So these are Volterra processes. Now, what are the second type of objects that we're going to discuss? Path signatures. They have been introduced in the 1950s by the mathematician Chen. coming from algebraic topology. And what are path signatures? They are simply sequence of iterated integrals. Okay, we're going to look more precisely at the definition later, but here I would like to maybe stress first that they play the role of polynomials on path space, right? So this is why we essentially like them. And today, okay, they are quite popular in fields such as machine learning and finance. They play the central role in rough path theory, and um, Terry Lyons actually um, worked a lot to make these objects popular in applications such as machine learning and finance. But I'm going to focus first, okay, before going into signature, I'm going to focus first on this polynomials, okay? And let's go back maybe to standard polynomials. Why do we like polynomials when at least we do math um, even before applications. First of all, because polynomials are universal approximators, you can think of Stone-Weierstrass theorem or Taylor expansions. So this allows you to approximate any function in some sense using polynomials. And so once you have, let's say, a function, you can think of, if you want solution to a PD, conditional expectation, all right? Um, Once you approximate it by polynomial, again, using the previous idea, okay, if you extend the space and you include the monomials, okay, you can see this polynomial as simply a linear function, right, on this extended vector, right? So polynomial is simply a linear function of these monomials, all right? If the degree m is also infinity, this corresponds in some sense to a power series, if you want. So polynomials help in this linearization, in some sense, step. And another interesting property of polynomials that we like a lot is that products are linearized. So the products of two polynomials is again a polynomial, of course, of higher degree, okay, but where the coefficients can be computed and are given by the Cauchy product, right? So again, product of two polynomials, again, a polynomial where we can compute the coefficients using the Cauchy product, right? And so for these reasons, okay, we feel that polynomials help us in this linearization step, right? Okay, but can polynomials be useful in finance? And I would like to maybe highlight the usefulness of polynomial on a maybe interesting problem in practice and very intricate problem in practice, which is the joint calibration of SPX and VIX. So this is a very intricate, I would say, problem in practice and challenging problem in practice. Which consist in trying to calibrate. So we have VIX, which is the index of the um, a volatility index of the S&P 500, if you want. We have options on S&P 500, and we also have options on the VIX. Okay, so we can bet on the volatility on the market. So these options are very liquid. And what do we mean by joint calibration problem? It's finding a model that's able to calibrate to both SPX and VIX options at the same time, right? And this is a well-known problem that has been addressed several times in the literature, but the related literature usually strongly agrees that standard one-factor continuous models are not able to achieve decent fits. So it's decent joint calibration on both options, SPX and VIX at the same time. And so this was our starting point. With Sean-Lee and Camille Long from BNP Paribas was to try to understand whether or not we can find a simple model that's able to jointly calibrate SPX and VIX, and if so, can we do it in a tractable way, right? Um, and this is just to give you an idea of the volatility surface of SPX and VIX that we try to calibrate. Okay, so we express option prices in terms of implied volatility, and you see on the left-hand side you have the SPX implied volatility. So bid-ask quotes are in dots, okay, red and blue dots. On the right-hand side you have the VIX implied volatility, and you see you have upward slope of the VIX. Um, and again, you have the quotes here, and you have the VIX future quotes, okay, which are the vertical lines here. And the green prices or implied volatilities here are not the bid prices, but the prices calibrated with our model, right? And this is a model that I'm going to show you later. But usually, okay, this problem is very difficult because I mean you have to match to have upward slope for the VIX, a steep I would say skew for the S&P 500, negative skew for the S&P 500. It's not very easy, okay, when you play a bit with the problem to calibrate the levels, the good levels to get the good levels of the fixed implied volatility. When you calibrate to SPX miles. Another also difficulty is also to match the term structure of the VIX futures as well as the term structure of the at the money skew of the SPX and at the money vol of the SPX. Okay, so this is a very difficult problem, and you see here, okay, this is um, I would say the short end of the um, volatility surface up to 3 month, okay, that we calibrate here. All right, and this model that's able to achieve this joint calibration problem is based actually on polynomials. Okay, and the idea behind this model is a one-factor stochastic volatility model for, if you want, the S&P S, driven by Brownian motion B, which is correlated with um, a Orshal-Uhlenbeck factor that will drive the volatility. Okay, so the idea behind the model is to say, okay, we will model the volatility, okay, as stochastic process. Okay, it's a function of a mean reverting process. Okay, this is the most basic, I would say, satisfact you would like to put for modeling volatility to have mean reversion. Okay, and the idea is to say how do we pick this function of this mean reverting process now. So we already know that if you take a volatility that's log normal, so meaning that uh, exponential of x, okay, for the volatility, this is, if you want the one-factor Bergomi model, this will give us very good fits on the short end of the S&P SMILE, okay, but we're not able to jointly calibrate SPX and VIX. And so the idea behind this model was to say, okay, you start with the exponential, which we know, okay, we get very good fits for SPX. How can we tweak it to get also good joint calibration for VIX miles? And the idea is simply to say, okay, you take the exponential, you expand it as a power series, and you let the parameters of this power series free, and you calibrate them to data, and you stop once you start to see a good calibration, right? And that's how we end up with this 5-order polynomial, and this is why we call it quintic OU model. I'm going to maybe later explain why the odd degree is important, okay, in this setup. But okay, so this is our model. I already showed you a fit for SPX and VIX smiles on one specific date, but this fit is actually not specific to the date because what we actually did was to did a daily calibration across more than 10 years of data. And here we plot the mean squared error on the option prices if you want. So the date I showed you was somewhere here. And you see that on all other dates in our data set, okay, we get a similar type of accuracy in green here. So we did this joint calibration over more than 10 years of data, so the result is rather robust. We also compared it to other models where we replaced, let's say, the OU factor that's driving the volatility by a rough process, okay, by keeping this polynomial of degree 5, but of this rough process. And you see the comparison here for the rough process, okay, in all market conditions, the rough process is in the accuracy of the mean squared error of the calibration is in red in all market conditions. Okay, the simpler model, one factor, or OU Markovian model outperforms in all market conditions, okay, this rough models. I'll explain a bit more later why these rough models do not work well when you calibrate to short um, maturities on SPX. At the same time, thanks to the polynomial, so the polynomial structure introduces some flexibility, but also introduces some mathematical tractability because the VIX in this model, thanks to the polynomial structure, I'm not going to detail it, but we have an explicit expression for the VIX because all we have to do is compute conditional moments of uh, Orshad-Ulmbach processes, and this we can compute explicitly. We can also price VIX by simple integration against the Gaussian density, pricing VIX products such as call and put prices on VIX. And since the model is Markovian, if you want to price options on SPX, you can use PDE methods. Also, Monte Carlo method is quite efficient in this setting. But can we exploit the polynomial structure to also get another method and more accurate method to price SPX products? And this is a question that we addressed with Shanli and Shriyang Lin. And the idea here, just to maybe identify this um, mathematical structure, okay, using these polynomials, maybe here we'll simply maybe generalize the model slightly, I would say, by simply replacing the polynomial of degree 5 by simply power series, okay, of the Orshad-Ulmbach process. By doing so, of course, we cover the previous case of the polynomial of degree 5, the quintic model. Also, the exponential now function is covered here. It's an example, okay, it's an extreme example, I would say, um, of this class of models. The other extreme is just taking p of x equal to x linear. And in this case, the volatility is linear, just an OU process, and you recover the celebrated Steinschein and Chauvel-Zoo model. Why do we like the Steinschein and Chauvel-Zoo model? Because for the specific case, when p of x equal to x, so the Steinschein case, we have access to the characteristic function in explicit form. The characteristic function of the log price, okay, is given explicitly and is given as an exponential, it's exponential quadratic in x, essentially. Okay, so said differently, it's affine in the augmented space x squared, where the coefficient psi are given explicitly, they are deterministic functions, and they happen to solve a system of Riccati ODEs. Right? Why is this interesting in practice? Because if you have access to the characteristic function of the log price, the characteristic function is the Fourier transform of the density. Fourier transforms are invertible, so this means by Fourier inversion of the characteristic function, you get access to the density, and now you can price options by Fourier inversion techniques. Okay, and if you want the Steinschein-Chauvel-Zoo model, this is the ancestor of the Heston model, right? And I think this is in the Steinschein paper. I think this is the first paper where these Fourier techniques were applied. I think in finance. All right, so this is for the case p of x equal to x, where we have this fast pricing and accurate pricing by Fourier inversion techniques. What happens now if you take more general p? For more general p, now of course the structure might break down, but you can use a similar idea and now say, okay, let us augment the space without additional, I would say, information. Let's add all the sequence of powers. Okay, so the infinite series. And let us expand the characteristic function or the log characteristic function as a linear function in these variables. So does this mean? This means that we're doing a power series expansion of the log characteristic function. And let us look for these coefficient psi as deterministic coefficient and see if this would work. So let's make this n-sense and see what type of conditions should these psi satisfy. All right, and in these expansions are also, I would say, related to other type of expansions of characteristic functions that appeared in recent papers by Chris Akiro, Sals Valutofero, and Yosef Teichmann, but also Peter Fritz, Jim Gadrell, and Redo Itchich. And if you write this ansatz, okay, and you apply Ito's formula, you end up with some infinite dimensional ODE that should be satisfied by these psi k. And these are nonlinear ODEs, and the nonlinearity is simply a square. Okay, so you see here there's the discrete convolution that appears, or the Cauchy product that appears in the red term here. Um, why do I say this is a square? Because recall when you multiply two power series, okay, you end up with a new power series where the coefficients are given by the Cauchy product. So this essentially comes from the product of two power series, okay, that we are linearizing, okay, and we end up with this equation when we apply Ito's formula, right? Um, and yeah, so we end up with this infinite dimensional equation because, okay, it's indexed by k, um, and um, and with this you can actually write a verification, I would say, result. So if you assume that you have an existence for these equations such that this series converge, okay, and additional assumptions, then you have access to the characteristic function, right? Um, and then you would like to understand, okay, theoretically, these assumptions are valid or satisfied, and this is currently a difficult question. There are partial results in the literature. We also had some partial results um, for this question here. But for now, I'll leave this aside. But even actually numerically making this work, okay, and applying Fourier techniques is not straightforward. Okay, why? Because typically what you need to do here is to truncate the series first, all right, and then you have a relatively high dimensional ODE to solve, but where the coefficients here, if you want, they increase quadratically with the dimension. Okay, so you see there are some stiffness also in this um, ODE, so it's quite intricate to solve numerically. Just to highlight this, if you apply, let's say, standard method like Honchkutta method, um, at some point, okay, these methods are unstable and you'll have some blowups. Okay, but using some techniques, we were able to stabilize in some sense the schemes, and we ended up with a more stable scheme, and we were able to make the numeric work here. Right, and just to highlight an example, if you go back to the quintic OU model, here by increasing the truncation, doing pricing by Fourier, okay, by solving this infinite dimensional Riccati equation, you see you have convergence towards the Monte Carlo prices that are in red in the quintic OU model, okay? And you can do the same thing now in the one-factor Bergomi model, so you can apply Fourier techniques to price in the Bergomi model. And here convergence is faster, right? Because the coefficients in the Bergomi model decay as factorial k, okay, this exponential expansion. Right, so we were able to make at least this method work for realistic set of parameters and make these Fourier pricing work. But this is again thanks to this polynomial structure of behind these models. Okay, so polynomial help not only for the flexibility but also for the tractability. All right, so now that we've discussed the importance of polynomials, at least um, for the specific problem in math finance. Now we're interested in understanding how to incorporate more memory. Okay, if you go back to our summarize and linearize strategy. Okay, now we know maybe a little bit how to linearize if we keep this polynomial structure, but how can we now summarize the information? Okay, the path dependency that we can have in our models. And this is where signatures come into the picture, actually. So what are signatures? So we already considered the sequence of monomials. Think of the sequence of monomials of the Orcha-Ulbeck process, but make it collapse through Brownian motion to linearize the pricing problem for the quintic model. Okay, and this sequence of monomials, we call it the signature of the Brownian motion. Of course, we can rewrite this sequence as a sequence of iterated integrals in the sense of Sretanovich, okay? Because here you recover the chain rule for this um, um, integration rule, right? Sretanovich, and so this double integral is simply WT squared over 2, okay? And so on. Now it's not very interesting, right, to rewrite this very compact sequence here as the sequence of iterated integrals here, right? Um, it's not very useful to do that, right? And why it's not useful? Because actually all of this sequence here is summarized simply by the value of the Brownian motion at time t. Okay, that's why this object here uh, is not very interesting. Um, the object would become more interesting if uh, it provide us with some information on what happened between 0 and t for the Brownian motion. Okay, so if it's able to encode in some sense information on the path of the Brownian motion between 0 and t, and not only the terminal value of the Brownian motion at time t. Okay, so how can you encode more information on the path of the Brownian motion between 0 and t? Well, you can simply extend, in some sense, this object by simply extending the initial Brownian motion. You extend it with a time variable s, okay? And now you compute the sequence of iterated integrals just like before, but now this augmented process, 2D process, right? So what happens if you do this? Well, the level 0 will be always 1. Level 1 will be the integral against ds and dw. So now you have vector, okay, two-dimensional vector, and you recover twt just like before. And now you take each of these components and you integrate them again against ds and dw. So you have two components integrated against ds and dw each. So you have four components, okay? The two extreme components, again, they give you just like before, t squared and wt squared, okay? But now the cross terms, when you take w, you integrate it against the s. Now you see, for instance, this cross term gives you information on the path of the Brownian motion. It gives you the running average of the Brownian motion between 0 and t, right? And also this guy gives you information, additional information on what happened between 0 and t. And notice that these two terms are not equal, so it's not symmetric, okay? Um, okay, so this is the second level. So we start to see some information on the path, okay, encoded in this object. And now you take all of these four elements and you integrate each one of them again against ds and dw, so on and so forth. And you see by adding these um, integrals, okay, and especially with these mixed cross terms, dw and ds, you'll add more information on the path between 0 and t, okay? And if you consider the whole sequence, this is what we'll call the signature, actually it encodes all the information that you have on the path, okay? It characterizes the path. And the signature plays the role, you can think of the signature as playing the same role as polynomials on path space, okay? So you can already see it here, okay? Some elements of the signature are exactly the monomials that we had before, okay? Plus some information on the path, okay? So this is one way if you want to see it, but it also shares a lot of similarity with polynomials, as I'm going to explain next. So it also has this universal approximation property. So now instead of taking just functions of wt, so this we know that we can approximate by polynomial in wt. Now if you take a functional of the path of the Brownian motion, okay, for suitable functionals, you can approximate them by finite linear combinations of signature elements. Okay, linear combination of signature elements is essentially the equivalent of or the analog of polynomial on path space. Okay, but you can also consider, let's say, power series. Okay, and then you end up with some analog of power series or entire function or analytic function on path space. Okay. And I'm going to go back at this question maybe later. What type of maybe uh, dynamics or function of the Brownian motion can we represent exactly in terms of these uh, infinite power series of the signature of the Brownian motion? All right, so you have this similar type of universal approximation uh, power. of the signature object, but now on the level of the functionals, okay? Not just functions of the Brown notion at time t, but function of the path of the Brown notion. Okay, so before discussing these linear combination of signature elements, okay, here we simply need to introduce, I would say, some notation just to be able to keep track of the indices or the terms, okay, that we're going to consider. So you simply need an indexation, okay? And one way to do it is simply to use words and letters. So use letter 1 to denote the first coordinate, time coordinate of the Brown motion, and letter 2 to denote the coordinate of the Brown motion. Okay, so you can represent, I would say, the signature objects in a more compact way, like this. Okay, so you have level 1 here, level 2, so words of length 2, level 3, words of length 3, and so on and so forth. Okay, and now if you want to extract an element of the signature, you simply hit the word against the signature. Okay, and so you see 1, 2. This means that you are level 2 of the signature. So you have two integrals and you follow the order of the letters in the word. So first you integrate in time and then in space. Okay. And so you end up with this object. To 1, integrate first dw, then ds, so on. Okay. To 1, 2, you get the idea, right? And now you can do finite linear combination of these elements, right? And this is how you extract finite linear combination of the signature elements. Okay. And so now, if you want to do, let's say, possibly infinite linear combination, okay, this is the same idea. Now you can sum over all levels, and level by level, you do finite linear combination, okay, like this. Now, of course, if you want to hit now a possibly infinite linear combination against the signature, here you have a series with possibly infinitely many non-zero terms. Okay, so you need to make sure that this series converge in a suitable sense. Of course, you have a power series. Okay, just like in the 1D, if you want case. And here you want to make sure that this series converge. Okay, this is not something that I'm going to discuss in this presentation, but if you're interested, you can have a look at the paper. So all the series that I'm going to show you have been proven to converge. Okay, in a suitable sense, right? When you have infinitely many, I would say non-zero terms. All right, so let me just recap what we just said. So um, again, signatures, you can think of them as simply analog of polynomials, but in higher dimensions on path space. Okay, so in 1D, what is the signature? It's simply the sequence of monomials. What is a linear combination of signature elements in 1D? It's simply power series or polynomial, okay? If it has finitely many non-zero term. It's the same thing at the level of the signature. You simply need a way to index things, but it's the same idea. What was really nice in 1D is that the product of two power series is again a power series where the coefficients are given by the Cauchy product. Okay, this is something we discussed earlier. What's really nice is that this algebraic property, you still retain it for the signature. Okay, so now the product of two linear combination of signature elements is again a linear combination of signature elements, but now you need just simply a rule to compute the coefficients, and the coefficients are given by the shuffle product. What is the shuffle product? It's simply, if you want to see it, simply the generalization of the Cauchy product to higher dimension. Okay. Okay, so the shuffle product will play the same role as the Cauchy product. Okay, it helps you linearize the product of two linear combination of signature elements. Okay, or two power series if you want. Okay. Okay, and then we discuss this approximation power, right? So I'm not going to discuss the shuffle product. Okay, this is just the I would say the formal definition, which I'm not going to discuss. Okay, but let me go back to the summarize and linearize problem that we had before, and now we already saw that the polynomials can help in this linearization step, but now since signatures encode also information on the path, okay, that will help in the summarization um, step, okay? And by summarization step, I mean building good Markovian variables to summarize the information that we have, okay? And to highlight this, I will give you some examples, okay, on how to encode or build Markovian variables from non-Markovian systems. So typically non-Markovian systems, okay, you can think of, let's say, some path-dependent equations or Volterra dynamics, okay? You can start from a process X that's non-Markovian. And here you could ask, okay, if you have, let's say, strong solution for this equation, can you actually um, explicit. So if you have a strong solution, we know that it's a measurable function of the trajectory of the Brown motion and time. Okay. Um, so one could ask, okay, under which condition can you actually express this functional in an explicit form? Okay. And by explicit here, I mean maybe a power series of the signature of the driving noise. Okay. Um, so this is basically, if you want, just doing some type of, if you're familiar with stochastic Taylor expansions, but proving that the series, um, in some sense, converge. Okay. Um, yeah, and this is if you want related to very nice paper by Jean Benarous in the 1980s who looked at this problem, but for SDEs, okay, for Markovian SDEs to expand, in some sense, the solution of SDEs in terms of analytic functions in the signature, okay, in some sense. But I think, okay, I think that this method becomes even more powerful when you combine it, when you apply it to non-Markovian systems. Okay, because the signature object is a Markovian object in infinite dimension, and so you start from something that's non-Markovian and you end up with a linear function of something that is Markovian. Okay, so then you can apply, I would say, the Markovian toolbox on this object, on this lift. All right, and this type of questions, okay, this is something we considered with Liu Mangera and Yuqing Yuang, and I'll show you some, I would say, concrete examples, explicit examples. Um, where we can express or linearize, if you want, or summarize non-Markovian processes, writing them as linear combination of signature elements. Okay, possibly infinite linear combination. Okay, so power series expansions. So the simplest object is, let's say, Gaussian process. Okay, so if you start from X, let's say Gaussian process, non-Markovian process with the kernel K, okay, think of Volterra process, and you take this stochastic convolution, you can very easily actually expand X in terms of a linear combination of the signature element by simply doing a Taylor expansion of the kernel K, okay? You do a Taylor expansion against T, around T, okay? Because even if you have, let's say, some singularity of the kernel at zero, you try to expand the kernel far from zero. Okay, so if the kernel is analytic, far from zero, you can simply do, let's say, power series expansion of the kernel, and this allows you simply to rewrite X as a linear combination of the signature elements here. Okay, by simply applying Taylor expansion here, and you see you'll get a sequence of ones and 1, 2. Okay, why 1, 2? Because when you expand the kernel in S, this is how you'll get the iterated integrals in the S variables, in the S variable. Okay, and you see that you only have dw appears only once, exactly one time in all of these expansions because, okay, K does not depend on W. Okay. Okay, and you can do this for the exponential kernel, you get an explicit expression. You can also do this for the Riemann-Liouville fractional Brown motion, and you can do this for the fractional shifted Riemann-Liouville fractional Brown motion. Okay, I'll show you one application later on of these expansions. But notice that, yeah, these infinite linear combination of signature elements are not always semi-martingales, okay, as shown by the example of fractional Brown motion. You can use this to simulate the process. Of course, it's not a very efficient way to do it because here what you could do is since you have the coefficients that are explicit here, L, they are deterministic coefficients that are explicit, you can simply simulate the signature, you truncate, okay, and you get an approximation of X, right? So you can use this to simulate the process. In this setting, it's not very interesting because, okay, X can already be simulated more efficiently. But in other configuration, okay, for more complex dynamics, one can use this idea. Um, and so let me highlight this on more complex dynamics. Okay, the same idea how to expand these systems in terms of the signature of the driving noise. So we're going to restrict to linear dynamics um, and start from an OU process just for simplicity. Okay, I'm going to highlight the strategy on the OU process, and the same strategy will work on non-Markovian processes. Okay, and the idea is very simple actually. The idea is simply to, in some sense, forget the probabilistic equation and recast everything in algebraic way. Okay, and how can we do it? Well, every time you see dt, you replace it by 1. Okay, because we're looking, okay, we would like to expand x in terms of linear combination of signature elements. Okay, and we would like to look for these coefficients, L, deterministic coefficients. So every time you see x, you replace it by L. Every time you see dt, you replace it by 1, okay? Because integration against dt is simply concatenation with 1. Every time you see dw, you replace it by 2, okay? And so you see here you have L on the left-hand side, right-hand side, um, and then you collect the terms that depend on L, um, and um, and you recognize that your P and Q, okay, P and Q are entirely determined by the parameters of the model. Okay, and here you have an equation on L, which is a linear equation. But this you can solve, at least algebraically, you can solve explicitly, okay, by simply inverting the system. Okay, you have a linear equation on L, you solve it, and that's it. Now you have an infinite series for L, as long as this now linear combination, infinite linear combination makes sense. Okay, you can prove that it's convergence. You can apply Ito to this process and show that it satisfies the SE. Okay, so by doing this, I would say algebraic translation, one is able to solve the equation in an algebraic way and get an explicit solution for X in terms of the signature of the noise. Okay, now why is this useful? Because if you forget about this SDE and I simply give you this linear algebraic equation, okay, without telling you what P and Q are, it's very difficult for you to tell me whether or not this equation comes from Markovian or non-Markovian dynamics. In fact, you won't be able to actually recognize unless, okay, look at the P, what P and Q are, okay, whether this corresponds to a Markovian or non-Markovian system. So this equation completely hides the Markovianity of X in some sense, okay? And so said differently, now that we were able to solve it for the OU process, actually the same structure will hold for more complex dynamics, non-Markovian dynamics, as long as you have some linear dependence in the drift and the volatility. Okay, and so this is what I'm going to show you. So all the solutions that I'm going to show you will be written as P times an inverse. Of course, P and Q will be different. They will depend on the parameters of the model, but all the equations will have the same, at least representation. In terms of the signature, and the coefficient will be given by P times an inverse. Okay, so for the OU, okay, this is P times an inverse. This is what we just did. You can explicit the coefficients, and you end up with the stochastic Taylor expansion of the OU process. Okay, except that here we just simply do it in one shot. Okay, we compute all the coefficients in one shot thanks to this algebraic equation. If you add now linear diffusion part, again, you get P times an inverse. Okay, we're still in a Markovian setting, but now let's move to a non-Markovian setting. Let's move to some Volterra dynamics. So now convolve the dynamics by some kernels, K1 and K2. put some additional structure on the kernels. Okay, let's assume that the kernels are um, weighted sums of exponentials if you want. Then the solution is also given, the solution for the system, you can also recast it in an explicit form in terms of the signature. Okay, again, you're able to decouple the noise from the system from the parameters of the model. And these parameters are again given by P times an inverse. Of course, P and Q are slightly more involved than before, but they only depend on the parameters of the model. Okay, and they are explicit and you can compute them. Another example is delayed equation. Okay, that's not the Volterra equation, this delayed equation when you put linear delay in the drift and the volatility. Again, it's a non-Markovian system, and again, the solution is P times an inverse. Okay, so you see all of these examples fall and can be treated, okay, in the same way. And why can this be useful? For instance, okay, you can simulate the process as I showed before, but you can also compute some quantities. So now, let's say I give you this system here and I ask you to compute conditional moments of y. Since, okay, already computing moments is not straightforward, right? Even numerically, let's say. But computing conditional moments, since y is non-Markovian, it's even more involved, right? But here, thanks to our representation, now you can actually compute moments, conditional moments, have a representation for conditional moments of this y or u or any system, okay, that you're able to write in these as linear combination of signature elements. And the idea here is simply, okay, to combine, in some sense, the shuffle property, which allows you to linearize products, okay, with the fact that the signature is, in some sense, of the Brownian motion is Markovian, and you can actually compute its expected signature or conditional expected signature in an explicit way. Okay, so now you get an explicit expression for the moments of y and u. Okay, and now you can truncate these, compute them numerically, and have a method to compute moments, at least implement moments of these non-Markovian systems in a very systematic and generic way. Okay, and now let me show you another example where we will exploit this linearization property of signature. So now that we know that this object is in some sense universal, okay, let's just simply take the quintic OU model in some sense and replace the volatility by now linear combination of signature elements, okay? And the idea here is to say, okay, now you start from any model, you approximate it, you approximate the volatility process by this linear combination, you end up with this signature volatility model. Can we come up with a generic method to do pricing of options on S, let's say? Okay. Yeah, this is also, I mean, this class of models have been actually introduced by Emmanuel Perez-Arribas, Chris Alvi, and Lucas Sprutz, at least in the additive setting, and later also studied by Chris Cucchiaro, Guido Gazzani, Bianca Moller, and Sarah Valuto-Ferro. And here, just like before, okay, thanks to this linearization property, you can have an expression for the characteristic function of the log price in these class of models, okay, modulo sum Riccati ODE. So here you see the characteristic function of the log price will be exponentially affine in the sense of infinite linear combination of the signature element, where the psi will solve a system of Riccati ODE, where you essentially replace the Cauchy product by the shuffle product. Okay, but here again, okay, I would say the questions of distance for these equations still open problem. But I'm going to show you maybe some numerical illustration of the importance of this result. Okay, and for this, I'm going to go back to a more realistic model, which is the Volterra-Bergomi model. So let's forget about signature for this slide, and let us go to the class of Volterra-Bergomi model, where sigma is simply given by exponential of a Volterra process. Okay, so you can think of sum of exponentials is the n-factor Bergomi model. You can have rough kernel, or you can have shifted fractional kernel. Okay, here. And of course, which kernel do you pick? Well, this depends on data, and usually the kernel helps you in capturing some term structures. Think of the term structure of the Edemani skew. Actually, if you plot it in log-log plot, you can actually see that the term structure of the SNP has some type of concave shape, which is not well, I would say, matched by the exponential kernel, at least for maturities between 1 week and 3 years. One time scale is not enough. Two exponentials allow you to fit this very well. Rough processes give you power law behavior of the skew, which in log-log plot gives you a straight line. And this is not what you observe in practice, so they are not consistent. So these rough models are not consistent with the Edemani skew of the SPX. One way to correct for this is to get rid of the roughness by simply shifting the singularity of the kernel. Okay, you shift the kernel, and then you end up with this orange line, and you get a very nice fit here. Okay, so the shifted kernel is a very good fit for this Edemani skew, at least on average. Okay, and this has already been identified by Lorenzo Bergomi, Julien Guillon, Elam Rani, and also Jules Delmotte and Stefano De Marco. And if you go back to even Bergomi's book in 2015, actually he introduced this shifted fractional kernel in this model to actually, okay, match this power law behavior for large maturities, okay? To quote Bergomi, he adds that unfortunately we lose the Markov representation and such models not usable in practice. And what I would like to show is that thanks to signatures, now one can make this model usable in practice to do pricing and hedging. And the idea is simply to recast this model as signature volatility model and apply these Fourier inversion techniques. So how can we do this? Well, you start from the shifted fractional Bergomi model. We already know how to expand this shifted fractional Brownian motion in terms of a linear combination of signature elements. This is what we did previously. And now you're interested in the exponential of this guy. The exponential is simply you expand it as a power series, okay? And now you apply the shuffle property. So shuffle property allows you to linearize products, okay? And then this will allow you to linearize the exponential in some sense, okay? So said differently, the Volterra-Bergomi model here can be exactly written as a signature volatility model with these coefficients. Okay, and so now you truncate these coefficients. These coefficients are explicit. You truncate them, okay, and you solve the Riccati equation, and now you can do Fourier pricing and hedging to approximate prices in this class of models. And now if you do Fourier pricing, you compare it to Monte Carlo, this is what you get, okay, at least for short maturities, it works pretty well. And now you can apply these also to do pricing and also hedging in this non-Markovian model. But thanks to the signature, now you have a Markovian lift, and now you can do also hedging in a very efficient and generic way.
Eduardo?
Yes.
Okay, sorry, maybe my internet was so you continued or not? I did not hear it anymore.
Yeah, do I still have time? Sorry.
Yeah, a few minutes, let's say.
Okay, maybe I can, yeah, maybe I can conclude with this problem, which is the truncation problem. Um, so how can one truncate?
I'm not sure if it's my internet
Question actually.
or
No, it's
Yes.
not only you.
okay, Bear, you also Eduardo, we could not hear in the last few minutes. Is it
Sorry.
maybe you yeah, just repeat what you were
Can
saying.
you, yeah, can you hear me now? Yes.
Yes, yes.
Okay, yeah, sorry for that. Um, Yes, so now a fundamental question in the signature volatility model is the truncation of the volatility, okay, component. Why? Not only in terms of accuracy, but there's a more fundamental, I would say, question in finance for us, which is really interesting and crucial before using the model in practice. Um, and essentially, okay, here you have local martingale, which might not be a true martingale because the volatility is not bounded. Okay, you have a local exponential martingale, and before using the model in practice, one needs to check um, for true martingality. Okay, and this question that we addressed with Paul Gassian and Dmitry Sotnikov. And so if we, let's say, put aside, I would say, the um, trivial cases where the correlation rho is zero or where we have just simply the first term of the signature, we were able to characterize true martingality of the stock price in these class of models. So the stock price will be a true martingale if and only if n is odd and rho is negative. Okay, and why is true martingality important? Because if you have strict local martingale, then you have this strict inequality here. Okay, this is a and this means that actually put call parity breaks down in a strict local martingale um, model. So in order to highlight this result, if you want, or illustrate it in practice, one could essentially compute prices of puts and calls and compute the implied volatility of puts and calls in the model. And the model will be martingale if and only if, okay, the implied volatility of puts and calls match, actually. And so one can see here that when n is even, you have a mismatch between the implied volatilities of puts and calls. When n is odd and rho is positive, you have a mismatch, and they only match when rho is negative. All right. So yeah, so we have this characterization, and to go back to the quintic model, this is why we took a polynomial of degree 5, okay, odd polynomial, just to preserve the true martingality of the stock price. All right. Um, okay, so I think yeah, um, I think I can stop here and leave some time for some questions. Thank you.
Thank you very much, Eduardo, for this great talk covering really a lot of topics. Really nice. I enjoyed it very much. Uh, are there questions from the audience? So so you can write or you can raise your hands and write maybe in the chat. So I do not see anybody. So let me start by one question, which I'm very much interested. You were speaking about these examples where you come up with an algorithm to solve these stiff Riccati equations for the example of the exponential of minus the Brownian motion to the power 4. And I was wondering, do you know if the truncated Riccati equation is actually well posed, and if the algorithm that you have then converges to this truncated one, or yeah, or is there a possibility that, I mean, we know that the infinite dimensional Riccati equation exists and is well posed, but for the truncated one, it's not so clear, and therefore I'm wondering if your algorithm, yeah, if you have some convergence to the truncated one.
Yeah, thank you, Krista. Yeah, actually, no, we don't have any theoretical guarantee that even for yeah existence of a solution for the truncated system, this is yeah much more uh, involved than the infinite dimensional one. And so for the truncated one, no, we don't have any theoretical, even yeah, theoretical guarantee that it exists. And we also did not prove anything about theoretical convergence, but at least numerically we were able to observe this convergence even on Fourier prices against Monte
Mm.
Carlo.
Yeah,
Um,
that's what I find impressive. And if it would be nice to have, I mean, even if the truncated one is not well posed, to have some convergence result of this of your scheme then to the infinite dimensional equation, for instance. And what is the dependence on the truncation level? So does it get worse if you truncate at higher levels with your scheme?
so actually uh, it it depends on the examples, but okay, we cheat a little bit in the sense that we cap. Let me just go back to the. Um, so okay, to stabilize a bit the system, um, we actually at some point, okay, we cap also these coefficients so that they don't grow too much with the dimension.
Hmm.
And this allows us to stabilize and not get this explosive, I would say, behavior.
Coming from this
That,
quadratic term, yeah. Mm.
yes.
Yeah, yeah, I understand. So therefore, it's not clear that it actually converges to the truncated system.
No, I mean, it's definitely not clear.
Yeah,
Even
yeah,
if we don't cap, it's not clear. Um, but numerically, it seems to
yeah, yeah. I know this.
work,
I find very nice,
um,
and it also
which
works
is,
for your signature models then.
and it also worked for the signature models.
And you use
Uh,
the same numerical scheme there, or
we used even much simpler scheme, but used this uh, cap trick, I would say.
hmm.
But we use much simpler scheme. Here we did something, we used some variation of constant. Um, we worked a bit more, we used this particular here structure, yeah, to build, I would say, more efficient schemes. So the scheme, yeah, in 1D is more efficient and um, I would say more robust than the scheme we used for the full signature.
Hmm. Hmm. Okay.